Right, shall we start? Yeah, I think it's 4:30, so let's start, right? This, I think it's in your notes, but anyway, I'm going to talk about deposits in engines and fuel additives, which are quite often deposit control additives. And basically, these are based on some of the, if you want to know more about this, these are the publications. I think you should all buy my book. On chapter 3 has this, but also there are several SAE papers, review papers, which look at that. You've got to bring it with you. Right. I don't know. The SAE, yeah, SAE sells them basically. Right. Okay. Now, deposits are very important in engines, in practical engines running normally. They form on all internal surfaces of the engine with use, and they can affect engine performance sometimes quite significantly. Okay? So what we'll talk about is the nature and formation of deposits, effects on engine operation, deposit control, and very briefly test procedures employed just to demonstrate to you that it is a very, not an exact science. And the first one, I'll first look at fuel and inlet system deposits, and then on combustion chamber deposits, which are really relevant to spark ignition engines. I will come to why it is so. In spark ignition engines, deposits can form on the valves, on the fuel system, and combustion chambers here. And some examples, for example, if you look at the, this is a clean injector, new injector, which was actually run in this long time ago in Toyota direct injection engine, Toyota Avensis, when they first introduced this in the European market, which was about 15 years ago. And this is how the injector looks, and this is the micrograph of what this, looking inside this slit, okay? Sorry, looking inside, I mean, that's the thing. And, this is the clean injector. And after 15,000 miles, this is how the injector looks. So deposits are formed outside and inside this slit, which is much more important because that's what affects fuel flow rates and so on. And you can see here deposits forming in here. And here is an example of inlet valve deposits. I mean, this is a clean valve, and you can have deposits which look like this. And in the worst cases, but this is not really common now, you can have deposits looking like this. And if you look at the micrograph, these are very porous, and these are, and remember that this, how porous they are, because the impacts of inlet system deposits in port fuel injector engines, it could be power loss because they restrict airflow and affect volumetric efficiency. And it could lead to, with port fuel injectors, these deposits could absorb fuel sometimes. So when you put the accelerator down, I mean, fuel doesn't come into the cylinder. So you have all kinds of poor drivability, poor cold start, increased emissions. All these things could happen. Once again, this was port fuel injection. Direct injection engines don't have the problem. But they could have much greater deposits than port fuel injector engines, but they have less effect. I'll come to that in a minute, okay? This is how the combustion chamber deposits look. I mean, if you just look at piston tops, you'll have this nice, smooth-looking deposits, and I'll come to that, I mean, how they can have other effects. But there are some general points about deposit formation. In general, all the deposits I showed you. Deposit levels reflects the balance between deposit formation and removal mechanisms. And these mechanisms are very different in different parts of the engine. For example, in injectors and inlet systems and combustion chamber deposits. And deposits in different parts of the engine affect engine performance in different ways to different degrees. The mechanisms involved are usually not very well understood because they're very complex. And the test procedures used, and this is one of the problems. These two are linked, actually, the last 2 points. The test procedures used are long, expensive, and often don't yield clear-cut results. I mean, you have to do a lot of statistical type tests. I mean, and they're very expensive, many of these test procedures. And general formation mechanisms. As I said, they're not very well understood. Just hand waving, you can say there are chemical mechanisms which basically cause deposit precursors. Quite often they are long chain hydrocarbons containing nitrogen and oxygen from partial reaction of fuel and oil components. Then they undergo thermal. What this means, by the way, you are asking me about nitrogen. Nitrogen is not a normal fuel component. It comes from small impurities or some small, so they can have excessive effects sometimes, not just nitrogen, there are other things as well in some deposit formation. Then the precursors undergo some kind of thermal decomposition, the rearrangement and so on, and there are further oxidation, molecular rearrangement, recombination. I mean, these are all just, there are changes happening, changes happen, which then finally produce deposits. There are physical effects also because things like blowback, liquid fractions go, which fuel fractions, condensation, surface temperature, all of these are important because they all affect the chemical processes, basically. So both physical and the chemical processes are important. Now let's look at different deposits, fuel system deposits. Injector deposits, they can, I showed you some pictures, they can plug injectors, upset the fuel flow pattern, and cause drivability problems. Okay? In port fuel injectors, this is an interest, this illustrates the differences between different deposit formation mechanisms. The injector deposit cannot be formed if the engine is run continuously, because if the fuel is going through the injectors all the time, deposits just don't form because whatever deposit precursors form, they're just washed away every time. Okay? So they need this special hot soak period when the injector temperature is high enough and the little bit of fuel that's left behind in the injector cooks, basically. But this is not the case in direct injection engines. Direct injection engines, even if you run the engines continuously, injector deposits can form. In fact, with port fuel injectors, when they first were introduced about, 25, 30 years ago, there was a lot of work done in, producing test methods. Like how much soak period, how much, what kind of speed and load engines should run at, in order to come to some kind of test methodology, right? And in terms of fuels, olefins and diolefins in the fuels are bad for injector deposits. It's particularly so in port fuel injector deposits. But they can be controlled by detergent additives. But this is much more difficult in direct injection engines because the environment in which deposits are formed is different. Because in direct engines, your injector tip is exposed to combustion products in the cylinder, whereas it's much less so in port fuel injection. Of course, we won't talk about carburetor deposits because they're not relevant anymore. In terms of intake valve and port deposits, as I said, if there is a port fuel injector, they can absorb liquid fuel, upset airflow pattern, and cause drivability problems, and also increase part throttle NOx. It's very interesting. In fact, this is one of the reasons why in the US, you have the US EPA has mandated the use of detergent additives in order to control port fuel port fuel valve deposit in the port fuel, which, because they said it increases NOx, and the mechanisms are not very well understood. It looks like these injectors deposit, valve deposits absorb heat and give it up to the fresh gas which comes in, and that increases the temperature and causes all these NOx problems. And in terms of formation, it originates by reaction of fuel and lubricant with hot exhaust gas and positive crank ventilation gases, which contain hot reactive materials, and then in terms of total level of deposits, direct injection engines have much larger intake valve deposits, because there is no fuel going past them. In port fuel injector deposits, fuel is injected in the back of the valves, and that washes off a lot of the precursors. So it's a very effective way of controlling deposits, actually. But still, in port fuel injector engines, these deposits form, and they're also much more important because they can absorb, as I mentioned to you, absorb fuel and upset the mixture strength in the cylinder. So, in fact, when I mentioned the Toyota Avensis, but before that, when the first Mitsubishi direct injection engines was introduced, there are massive problems with valve deposits, because there's no way. All the mechanisms of formation were there, but there's no mechanism for removing the deposits. And in fact, many people, I amongst them, thought this would be a killer for the direct injection engines. But they solved the problem by simply controlling. There are various, I won't go into this. But anyway, the deposit levels are much higher in direct injection engines, but they have much less effect. Because initially the valve deposits were so high that they were affecting the flow inside the engine, which meant because the mixture formation is so critical in direct injection engines, especially in stratified direct injection engines. So if you upset it, the whole thing goes. In fact, that was a problem initially, but that's been solved now. And things like olefins, diolefin contents, there is a lot of empirical tests done. There is a lot of data on what kind of fuel properties matter in producing deposits. But they can be controlled by detergent additives. And as I said, in the US, it's mandatory to use a minimum level of detergent. Right. Combustion chamber deposits. Again, as with all deposits, it reflects the balance between formation and removal. By the way, the time scale over which deposits are formed are very long. They are talking about tens of hours of engine operation, at least. Quite often test methods run the engines for about 60 to 100 hours in order to, and I showed you data where the pictures where we had run the car for 15,000 miles. That's when the deposits stabilize. So it's not an instant thing, deposit formation. So this is a dynamic process over some time scale, and it's to an extent reversible process. If you form deposits in combustion chamber, this is true about others, but more so with combustion chamber deposits, you can actually reduce them by running the engine in a different way. And with normal fuels in modern engines, they are primarily formed by fuel, but oil also contributes, because if the oil uses, for some reason, when the engine is not operating well and it's using a lot of oil, you will produce much more deposits, because oil is much more potent in producing deposits. Why is explained by this. Basically, the mechanism, it starts by condensation of deposit precursors onto the surface. And this is the limiting factor. I mean, the temperature of the surface in relation to the boiling point of the deposit precursors. And the other thing is, these deposits are very good insulators, so that as they start building up, the surface temperature increases. And that reduces deposit formation. And this is why combustion chamber deposits don't fill up with deposits. They're limited to a certain level. Each fuel has a limiting surface temperature. For gasoline, it's around 310 centigrade. So if the temperature of the surface, whether it's the metal surface or the deposited surface, if the temperature is greater than this, no more deposit forms on this, because there's nothing in the gasoline which will cause this. But if it's oil, lubricant, which is heavier, it can add to this. So this is why lubricant, but in modern engines, if the lubricant is not being, coming into this engine, it won't matter very much. So what are the factors that affect deposit growth? Any change in engine parameters that increase surface temperature, like increase in speed, load, coolant temperature, will reduce deposit growth. Okay, I mean, very interestingly, making the mixture strength richer than stoichiometric actually reduces deposit formation, combustion chamber, because of the increase in combustion temperatures. And again, using materials of low conductivity like ceramics, which there's a lot of work done on trying to reduce combustion chamber deposits by using ceramics. This is because the surface temperature goes up and you don't produce as much deposits. And fuel and lubricant factors, as I said, boiling point is the most important fuel property. In general, the higher the final boiling point, the greater the deposit formation. And paraffins, olefins, and aromatics rank in that order for increasing deposit formation for a given boiling point. But of course, the aromatics in general in gasoline have a higher boiling point anyway. So, but in practical fuels, this is difficult to separate from boiling point effects, actually, because gasoline is so complex. And fuel detergent packages, which are, I said, needed to control injector and inlet valve deposits, usually increase deposit growth because these detergent packages are heavier than the gasoline, generally speaking. They are high boiling point materials. But there is a large variation between different additive chemistries and so on, and some companies make a big deal out of the fact that their additives don't produce that much deposits. Some of it is justified, some of the claims are not. And properties of combustion chamber deposits have been measured, some with very clever experiments. And this is the interesting thing. Compared to the fuel and lubricant, deposits have much greater concentrations of oxygen and of nitrogen as well. So they undergo a lot of changes in the combustion chamber. And the heat capacity has been measured, density has been measured, and it all depends on where the deposits are formed. In some, depending on whether they are the exhaust valve, because there's a big variation in deposit properties in the combustion chamber, depending on the surface temperature locally. Thermal diffusivity has been measured, and therefore, in the hotter regions, the thickness is much lower, like near the exhaust valve, for instance. And the porosity is very different. All these things have been measured. And these are, they've been measured for good reasons. I mean, because they're trying to connect the effects of combustion chamber deposits to their properties and so on. And what are these effects? Essentially, they increase the charge temperature and because of the flame propagation rate. I mean, you can measure this, in fact, as deposits grow in the engine. And they are very good insulators. They reduce the heat loss to the coolant. And they also reduce, for the same reason, volumetric efficiency. And they may affect the final phase of combustion through chemical means. I mean, but because of the higher temperature, they increase the octane requirement. That means an engine which is tolerant to knock, once the deposit forms, will start knocking, basically. They increase nitrogen oxides, and much less certainly, I mean, because it's not very clear, hydrocarbon emissions. In some experiments, hydrocarbon emissions go up. Some experiments, they come down. In some, nothing happens. I mean, there is a lot of experimental data like this. This is because there are multiple mechanisms. They can absorb fuel. Because of high temperature, they can, the oxidation of hydrocarbons can go up. So there are all these competing effects, and depending on how you run the engine, what the engine design is, you might get different results. But NOx always increases, and this is the most interesting part, actually. They sometimes very significantly can improve fuel economy. Because this is an area, I was talking to Rolf yesterday, I'm saying they should really investigate this properly, I mean, in terms of mechanisms. There's no doubt that they improve fuel economy. Anything between 2% and 15%, okay, in actual road tests and engine experiments and so on. Because it looks like the most important reason is they reduce heat loss to the coolant, and you can measure this. I mean, I published papers where you actually show that as deposits build up, the heat, that the heat flux decreases from the combustion chamber, and at part throttle, heat loss to the coolant is a very big contributor to inefficiency, basically. But it is a bit more complicated than that. But what is absolutely clear from empirical experiments is that fuel economy increases. And in fact, it's a well-known fact that compared to a brand new car, a car after use is much better in fuel economy. It improves in fuel economy. Traditionally, it has been thought of as, well, it's because everything gets bedded down and the friction reduces, etc. But that's not, in my opinion, combustion chamber deposits are the biggest reason why fuel economy improves. And sometimes, if the volumetric efficiency is decreased too much, there is a reduction in power. And this is an extremely interesting point, which I will now talk about. In the next, not now, but next one. There is very clearly octane requirement increase, as I mentioned. It becomes more prone to knock. And there are various mechanisms. One is simply volumetric, because the deposits occupy a little bit of space. I mean, they have some thickness, and they increase the compression ratio. But this effect is quite small, less than 10% of the total. Main effect is thermal, because the incoming charge is heated, because deposits, when the fresh charge comes in, the deposits have absorbed heat from the previous cycle, and they give it up to the fresh charge and increase the charge temperature. And there are also some very interesting, not fully understood chemical mechanisms. Probably we have some evidence. I mean, we published several papers when I was at Shell about these things, but it's not very clear what it is. I mean, it could be that they absorb, pro-NOx species, like maybe peroxides or something, and give it up during the later in the cycle. And because NOx occurs near the surface temperature, near the deposits, they have an effect. I mean, there's very clearly there are other effects, like during the era of leaded gasoline, where it was much clearer. I mean, that there are chemical effects because leaded deposits with lead in them were suppressing, NOx. ORI actually does not simply correlate with deposit weights, octane requirement increase. And piston top deposits have little effect, whereas end gas deposits have much more effect on this. I mean, you can do these experiments by, selectively removing some deposits and testing the engine again and so on. And different additives have different effects. I mean, but the problem is this ORI testing is long, costly, poor repeatability, reproducibility. And to come to sound conclusions, you have to do a lot of experiments. repeat experiments. I mean, this is the problem with deposit studies. In terms of engine performance, as I said, they could increase, they have an effect on HC emissions. Increasing surface temperature should reduce hydrocarbons, and plugging of crevices, by deposits must also reduce hydrocarbons, though there is not much direct evidence for this. It is just speculation. But absorption of unburned fuel and release later could increase hydrocarbon emissions. So there is several competing mechanisms which can affect this. And so the result is not very clear. Whereas NOx emissions always increase because the temperature increases. And removal of combustion chamber deposits actually reduces NOx levels. You can test this. And once again, piston tops deposits have little effects, and head deposits have much more effect on NOx formation, NOx increase, I should say. As far as carbon monoxide emissions, there's no credible mechanisms or convincing evidence that they have any effects on combustion, combustion chamber if deposits have any effects. As I said, they have real benefit on fuel economy. This is showed in multiple tests. Improvement ranging from 2 to 15%. And it is probably, there's faster flame development, no question about this, because you can again measure this. And heat loss to coolant is reduced. But it's not very clear exactly how this happens, what the mechanisms are. But it needs to be, this is a good area to study. Maximum engine power could be reduced, but this is, most of the reported studies are pre-1971. I don't know I have not come across anything recent in this kind of thing. Probably modern engines are not so, affected by this. Now, this is a very, very interesting problem. Okay, combustion chamber deposit flaking. This keeps coming every 25, 30 years, it looks like. And some people absolutely believe that this is the most important deposit problem in, in engines. About 15 years ago, yes, about 15 years ago, maybe about 12 years ago, there was a huge problem in the UK. I mean, with, I'll name the companies now, Jaguar, BMW, and Audi, very high-end cars. Okay, and basically they had this problem following a short drive and a long park, if you mean. So people would in winter, and it was almost exclusively at winter, in the winter. Okay, so you would just, you'd have parked your car outside your house, and in the evening you just put it in the garage, very short distance drive. Next morning you come to start it, it won't start. Okay, and this is because deposit flakes were formed when the engine was not running. I'll show you in a minute some pictures. And then when you start the engine in the morning, these flakes flew off and got lodged between the valve seat and the valve, in the exhaust valve, and you lost compression basically, and so the engine wouldn't start. And it is a huge issue because then you have to completely, open the engine, clean the deposit, then the problem could occur again for a few months later. In fact, Jaguar had this problem where they would drive the cars for export to come to the US, and they couldn't drive them off the ships, that kind of thing, And it made, I'm naming these companies because this is not a secret, and because there was a huge the press got onto it, this headline news in, in many of the people, because these are very expensive cars. You spend a lot of money, 4 months later your car won't run, start in the morning, And this is a very extreme case of this deposit flaking. But it could become more easily recognized as onboard diagnostic systems become more widespread, because hydrocarbon emissions will be going up and so on, because there's leaking from the valves, And as I said, I won't name him, but one of my, somebody I respect most in the engineer, he always told me that in their company, he thought more than 50% of recalls that they had, I mean not recalls, I mean the complaints they had and warranty were associated with this problem. And in fact, I got an email 3 years ago from somebody in China saying they had seen my papers and said, we have got this problem now. But, now, let me show you some pictures. Okay, this is a test that I devised to look at, I mean, it's an engine, the car test. We took this car, ran for 300 miles, 3,000 miles, opened the engine up, and this is how the deposits look like. And all you do is spray this with water, okay? And a few minutes later, this is how it looks. And sometimes, I mean, when this is from the car, but I had an engine test as well. And in the engine test, we take the open the head and spray the deposit. As you're watching, sometimes these deposit flakes could actually jump off. I mean, so it's as if there is some kind of, they are under some kind of tension. It's like a spring, okay? And you suddenly release the thing, and it jumps off. So this is how, so you can imagine if this had become this overnight and you start the engine, one of these flakes could come and lodge itself, right? Here is another example of another car. I mean, it's the same model. I mean, and this looked like this after spraying with water. And there are, I published 3 papers here, and there are lots of experimental work done to, make sure that it was in line with field experience. I mean, because these problems are coming from the field for these companies, and they are saying, for example, it happens in winter. I mean, there is a real peak in the winter and nothing in the summer, for example. And we established a way of quantifying the flaking, and so as to establish the test variability. And we found that there was wide variation between fuels. And it was definitely dependent on how you, I mean, what the cycle the engine ran, how the deposit was formed. So the environment, thermal environment for deposit formation was important. And we found that detergent additives, which are used for other things, as I mentioned, suppress flaking, And the flaking was directly linked to the loss of compression and startability problem in these tests. I mean, I won't go into the details. And you can also read, I mean, these are the 2 review papers I published on deposits in general, so there's a lot more data on this, okay? Now, what about diesel deposits? Most important deposits in diesel engines are the injector deposits. They are always occurring in the field, and they reduce maximum power simply by reducing the amount of fuel that comes into the cylinder because they restrict it. And in fact, this is the test procedure that you use to characterize deposit formation in diesel engines. There is in Europe, there is a Peugeot engine that is used, and you just run it full throttle continuously, okay? But the diesel fuel has to have some zinc additive. Otherwise, it won't form any deposits. And actually, it's not very clear why it is that zinc additive is needed. But of course, we know that in the field, deposits form. So what you do in this thing is basically, as you were, I think it's 80 hours or 100 hours, I know. I don't remember now. But the maximum power will come down, basically, in these tests. And that is the measure. That's how you measure deposit formation. And then if you put a detergent additive in the fuel, that doesn't happen, basically. And that's how you rate how effective the detergent additive is. And then there are internal deposits occurring on surfaces which do not see combustion products. I mean, like inside the injector. I mean, which cause needle sticking, and these can be very serious drivability problems. If the needle in the injector doesn't move, I mean, you just don't have any control over it. I mean, in fact, sometimes there won't be any fuel. I mean, there have been massive instances in southern Europe where diesel cars were engines, trucks were just coming to a stop because of this problem. And not internal deposit, but the deposit plugging can be controlled by detergent additives. Once again, the test methods, as I just mentioned, are very difficult and expensive. And I think after about 5 tests, the entire engine has to be changed because, you know, it can't stand that kind of operation. Mechanism of formation not understood, I mean, especially for internal deposits. And effects of engine operation need to be understood better, I mean, especially on internal deposits, okay? So what do they do? I mean, as I said, if the holes get blocked here, it can affect spray pattern, you know, and needle stem lacquering can. So this is the new injector. This is the foul injector in a diesel engine, for example. And this is not so bad, but it can be worse than this, you know, and it can affect spray patterns. So this is a clean injector, and this could be a deposited injector, you know, and that, as you can imagine, can have a big impact on the engine operation, especially on emissions. And here's another picture where, where without any additive, this is how it would look after, I don't know how many hours of running. But if put additives in, I mean, it could be much cleaner. I mean, this is, remember, this is outside the hole. But inside the hole also, there will be a big effect. And in terms of internal deposits, this is what you mean. I mean, for example, internal deposits could occur in surfaces like this, where is that? I mean, here, for example, you know, or here. And the arrow is not pointing in the right place. But anyway, it can make the needle stick and not move very freely. So now we come to fuel additives. Incidentally, if anybody is interested in fuel additives, this is an excellent source. I mean, this is from the Association of Additive Manufacturers, basically. This is a very good source of information about additives. What are fuel additives? They are chemicals added in relatively small quantities. It's generally accepted that it should be less than 0.5%. I mean, I would say 0.2%, basically, to be an additive. Anything more than that is not an additive, which is a fuel component, essentially. Okay? They are there either to improve fuel performance or to correct a deficiency. That's what additives are used for. And they're usually added as a package with, they're multifunctional, more than one chemical along with a solvent and diluent like xylene or gasoline in order to make them injectable, basically. And typical injection rates are 1,000 ppm to 1,500 ppm for the whole package, of which the more than half, actually I said up to, more than half the package could be simply solvents, like xylene. And they're usually added at fuel distribution depots by individual oil companies. Because, by the way, most oil companies, when they sell the fuel, they take their fuel from the nearest refinery, which may not belong to them, generally speaking, because otherwise it would be too expensive. I mean, you know, you can't supply, fuel in one part of the country from a refinery owned in another part of the country. And quite often, they have their own depots where they inject their own deposit, the additives. And usually now, the additives are manufactured by specialist additive and chemical companies, people like Infinium or Lubrizol or something. Previously, oil companies themselves used to manufacture them. But now it is all specialist companies doing this. And what are these fuel additives? In terms of performance additives, there is deposit control additives, very, very common. Almost all fuels in OECD countries have these deposit control additives. And in fact, as I said, in the US, it's mandated. There are combustion modifiers. Anti-NOx are the most important additives. Unfortunately, we don't have any credible anti-NOx additive at the moment. Once lead went out of the picture. Manganese is a very, I mean, we'll talk about it tomorrow, maybe not tomorrow. Manganese additives are also effective, and but there is tremendous resistance from auto companies to the use of manganese additives, though they are used in some countries, by the way. I think Brazil uses them, and not South Africa, Brazil still uses them, I think. But in fact, the manufacturers of manganese, Ethel Corporation, I think, makes them. They really fought to make sure that they were still could be used. But I think now they've lost the battle probably, because most oil companies will not use them because the OEMs are so much against them, basically. And friction modifiers are more recent, and they are used to reduce friction in the engine. They are mostly come from the lubricant additive portfolio, but they can put them in gasoline engine, fuels to reduce friction. I mean, that actually brings about 0.5% to 1% improvement in fuel economy, basically, by reducing this. Then there are storage and distribution additives like dehazers in gasoline, because quite often if water gets dissolved, I mean the gasoline gets cloudy, and you have to stop that, basically. And biocides are interesting. Sometimes they're used because when lead was in the fuel, I mean, they didn't have to worry. They killed all the bugs, basically. Yeah. But sometimes in storage and distribution, I mean, I've known about a case in Texas, for instance, in one of the Shell storage tanks, where basically this bacteria started growing, and plugged everything up, And sometimes but I don't think it's very commonly, the solution to this is make sure that there's no water in your tanks and keep the system clean, basically. That's what the solution is. Markers and dyes are quite commonly used to either to prevent fraud or to, identify their fuels for some reason. Antioxidants are sometimes used. Many of these, particularly in diesel fuel, many of these additives, as I said, are multifunctional, rather additive packages. So they usually contain more than one active component. And in terms of detergent packages, what are detergents? I mean, they are surface active materials, essentially a hydrocarbon soluble polymer connected through a suitable linking group to a polar head. The polar head is the important thing here. And they have carrier fluids, high boiling point, thermally stable solvent, and a dehaze. I mean, this is what a detergent package might contain, a multifunctional detergent package. Dehazer prevents suspension of entrained water, because some of these polar materials can promote that. So you have to, counteract that. And the mechanism is believed to be this. The polar head attaches itself to the deposit precursors, and then the tail gets dissolved in the fuel, and they take everything away, basically, But this is the thing. Sometimes these package components can interact with fuel and cause increased deposits somewhere else. And this was, by the way, a big issue when port fuel injectors engines were introduced about 25 years ago, because they found that there were problems. I mean, they have with injector plugging, and as I said, so they put detergent additives in them. And what were the detergent additives at that time? The ones they knew about were used in carburetor engines, and they were low molecular weight, smaller chain molecules. When they put them in, they suddenly discovered that the inlet valve deposits just increased in, basically they just increased. So the additive companies then worked to develop better additives for this kind of So there were large, higher molecular weight additives. And testing is once again extremely expensive and complicated and doesn't, and there are many industry standard bench and road tests. For example, in the US, Southwest Research runs what is known as the BMW test. I mean, it was done on a BMW. They have to go around San Antonio on a in a fixed route, and you just measure the amount of deposits that are formed. I mean, and that was a requirement in the US EPA, that they had to form, any new detergent package must pass that test. So actually people got very clever at finding the right, right car and the right BMW in the fleet, which would respond to their additives and so on. And with the diesel fuel additives, there are ignition improvers, which are very common. These are, EHN, for instance, hexaethyl nitrate is very commonly used. Then cold flow additives, which are very important, by the way, in diesel fuels in cold countries, because as I mentioned, they can, paraffins can just form waxes. They're plate out at low temperatures, and you need to, without cold flow additives, sometimes you can have serious field problems. Lubricity improvers. Lubricity is a big issue. I mean, especially in diesel fuel. It became suddenly a major problem when sulfur was taken out, because something that you did with hydrocrackers, which reduced sulfur levels, also reduced the lubricity of diesel fuel. And in Sweden, it showed up first because they reduced sulfur first. And within like about 50 miles, your injection system would be ruined, because your fuel pumps would be completely ruined because there's no lubricity. So lubricity additives are very important. And just as a matter of aside, very interestingly, if you put 1 or 2% of biodiesel, it takes care of all this problem. Biodiesel is extremely effective as a lubricity additive. And detergents are also used, I mean, they're not used, they're essential in diesel fuels. And there is a lot of things, sometimes odorants, I mean, perfumes have been put in diesel engines, Anti-foam additives are very common. Corrosion inhibitors are very common. And in terms of how much you put in, you put hundreds of ppm of these kinds of additives, whereas corrosion inhibitors could be less than 10 ppm. Very small amounts will be quite effective. And commercial additive package development is a very complicated and expensive process, because you do research and development, testing, and market trial. You have to do this. You have to collect evidence of benefits. Quite often, fuel companies do this because they want to market fuels. I mean, as a marketing exercise, they want to say that our fuel is better than everybody else's. And therefore, they need to collect evidence for the benefits of product claims. But this is the most important thing. You have to check for all kinds of side effects, including things like paint staining and toxicological, obviously, impacts. And this takes a lot of work, And this is where nowadays what the oil companies say to additive companies is, look, if you want to sell it, you bring evidence for all of these things, basically. Otherwise, I mean, eventually they will also do their own testing quite often to make sure that whatever they send out in the market is not going to be bad. I think this is it. This is my last slide. Thank you. Okay? Right.
So I have two questions.
Yeah.
The first question.
Mm-hmm.
10,000 miles.
Yeah.
Images.
No. It's a road test. It's a run on the road, everything included. But you know, but there are engine tests which are steady state tests. There are always differences, because if you run the engine in a hot test mode, you'll form different types of deposits to, you know, and this is, I mentioned this with combustion chamber deposits, for instance. Even combustion chamber deposits, flaking, etc. It depends on how you have run the test. Yes, it's very important. Yes. Hmm. Are you from Saudi Aramco?
Yes.
Yeah. See.
No, Saudi Arabia. I'm Saudi, but I'm not.
Okay, you're not from Aramco. Okay. Well, Saudi Arabia at the moment does not have any detergent additives in the package, and I've been saying since I joined them that you must put them in there because it's important, you know. But there are plans to put detergent packages in detergent additives in fuels very soon. Okay, but I mean, what was the other question about engines? Well, I mean, you know. Yeah, there is, since I joined, we have really expanded quite a lot. I mean, there is tremendous amount, especially there's a lab now in Detroit as well, and we have one in Paris. And I shouldn't say we now, I'm not part of Saudi Aramco anymore, but then there is a lot of work being done in Saudi Arabia itself, but there's a lot of work aimed at developing fuel engine systems, which I'm going to talk about tomorrow. Fuels and engines together. Yeah, I mean, see, fuels don't have an existence outside engines, and engines don't have an existence outside fuel.
But they will
No, only for reciprocating engines. Yeah. Yeah. Hmm. Well, I mean, basically, there is some theory. We did a lot of studies on this, including in in Manchester University. They have a very sophisticated electron microscope, environmental microscope. We try to understand what the mechanism was, whether there's physical or chemical. I mean, you know, essentially what it is, what we know is that when you spray water on this, it goes to a certain, I mean, it penetrates. They absorb water, okay? And the way it looks like is that, these deposits are formed, and they have gone through thousands of thermal cycles. And they are held under some kind of tension. And it's as if it's like an elastic band, and when the water gets it, it breaks it, whether it happens because of the solubility issue, or we don't know yet. I mean, we can't work it out. But what the detergent additives seem to do is that they change the structure of the deposit, maybe the porosity of the deposit, that the absorption of water becomes more difficult. So the structure of the deposit changes, and therefore they won't flake as easily. Well, we did all kinds of things. We tried to spray fuel, for example, but water is the most effective thing. And this fits in with the the actual field experience, which is to do with this short drive and long park. In fact, it's very interesting. Volvo, I mean, about 30 years ago, had the same kind of problem, I was told later. And they had what they called lawnmower tests. So they used, lawnmower test in the sense, they called it the lawnmower test. Basically, the engine would be parked, I mean, the cars would be parked, and they would move the length of a lawn in the winter. And they would just leave them there. Next morning, go and try to start them. And they had the same problem. I mean, No, this is completely cold. I mean, it's cold. Yeah, and left it overnight. Sometimes, actually, this is another point.
You didn't disassemble.
Yeah, we ran it for 3,000.
Then you disassemble.
No, we ran it for 3,000 in this particular test, 3,000 miles. Deposits were formed, right? Disassembled the engine, left it outside. I mean, to be next day, sometimes 2 days later. In fact, once we had left this pistons exposed to the thing for about 3 days. There was a bank holiday Monday. When we came back, without spraying the water, they had flaked, basically. So they had probably absorbed water from the atmosphere. But this kind of change happens like you're watching, in fact, the other thing is the water had to contain a little bit of, domestic detergent because that helped wet the surface. No, it's just huh? No, in fact, what we used to, in this case, what we used to do was the little spray things that you use for spraying plants, we just sprayed on this. That's it. And in fact, we also did experiment in the engine experiments. It's described in some of the other papers, where you take a drop of water, and not spraying like here, drop of water, put it on the surface. And this is what leads us to believe that it absorbs, So sometimes, you're just watching it, and this blob of water will be standing there because of surface tension or something. And suddenly, it'll get absorbed. And a few minutes later, these flakes will come out, And in fact, this is why then we started adding this detergent, domestic detergent too, so the blob of water doesn't just stand there. It just immediately spreads, Sorry? Yeah, I showed you. They are there. Yes. Sorry? Short drive is, the theory is that when engine is completely cold, like almost below zero, the outside temperatures, you drive a little bit and you form some water during the combustion. And that doesn't evaporate, that condenses on the, and that's why it is very prevalent in winter. Well, I don't know. In fact, the people in Jaguar claim they can make every single, they were doing a lot of testing, by the way, and they tried every single car model. They told me, I don't know whether they actually did that. Every single car model had this problem, they said. And in fact, one of the interesting things they used to do to understand this, compression loss, they used cornflakes. They threw cornflakes in the cylinder, And they actually they also showed us some videos, without the cornflakes, but they actually had videos of these deposit flakes coming into, that flying in the cylinder. Yeah. Yes. Yeah. Yeah. But it takes a long time. 3,000 to 5,000 miles, depending on the test procedure. Okay. Thank you.